Assalamualaikum and good day everyone. I am Dr. Nur Aisha Ahmad Shah from University Pertahanan dan Nasional Malaysia. I would like to share with all of you about the research that we have done, dipolar thiazole derivatives as potential optical materials. So as been mentioned in the title, optical materials, optical effects can be linearly and non-linearly or linear only. To make it clearer in this project, the interest is to study the potential of material, which is thiazole derivatives, to study their potential in having good NLO effects or specifically second order NLO properties. Therefore, I would like to give a brief fundamental introduction about what is nonlinear optics, NLO, what make a material can have nonlinear optical effects. So this is the optical phenomena that occurs when strong electrical fields interact with the matter. Okay, for example, the strong electrical fields such as a laser, which has a very strong or very high intensity. Okay, so it causes, because it is too strong, it causes the electron density distribution of the matter distorted non-linearly with the magnitude of the field. So therefore, the light that has interacted or passed through the NLO materials, they come out as new electromagnetic field components such as with differing phase, frequency, amplitude, etc. So for example, one of NLO effects is second harmonic generation phenomena, SHG, in which two photons with the same frequency interact with the NLO material, so it generates a new photon with twice the energy of the initial photons. So that's why we call it also as a frequency doubling. Organic NLO materials, depending on the applications, the advantages in using organic NLO materials over conventional inorganic NLO materials it has large NLO susceptibilities, it has a higher laser damage threshold yet lower in dielectric constant, faster response time as the electronic polarization of the pi electrons of the molecules are high, and the synthesis of organic compounds is tolerable. Therefore, this allows the versatility of molecular structural modification that leads to optimal NLO properties. In push-pull organic molecules of interest in quadratic or second-order NLO applications, the major hyperpolarizability component usually lies along the dipole axis. So by adding the electron withdrawing group and electron donating group that connecting by the pi system, a push-pull molecules, which is dipolar molecules, can be synthesized. Thiazole is a heterocyclic compound that contains both sulfur and nitrogen. Among organic containing pi system molecules studied, 1,3-triazole has been approved to have significant NLO properties by previous studies. Therefore, in this research, we want to further study with different structure arrangement and combination of electron withdrawing and electron donating group. So this is a very fundamental at molecular level. We try to design a new molecule in such a way it could have a second order NLO potential. Therefore, thiazole and benzothiazole has been designed to be incorporated with strong electron withdrawing group, which is nitro at one end, and electron donating group, amine, at another end of the molecule to form a dipolar molecule. So this thiazole will act as a pi electron bridge that it has the benefit it can lower the delocalization energy, which offers better conjugation, enhance the charge transfer properties, and also it has good thermal stability too. So in this study, we have successfully synthesized 8 new thiazole derivatives with different combinations of electron withdrawing group and electron donating group, and 5 out of 8 will manage to be recrystallized. The thermal stabilities of the synthesized compounds were evaluated, giving compound 1 and 2 are the most stable at high temperature, in which the compound started to decompose at about 280 degrees Celsius, while compound 3 and 4 started to degrade at about 200 degrees Celsius. And then the linear optical properties, we have analyzed their absorbance in the UV vis range. The UV spectra of all synthesized compounds comprises of a mixture of pi to pi star and n to pi star electronic transitions. So in this slide, we only showed compound 1, 2, 3, and 4 absorbance. So because we want to see clearly the difference of the structure and electron donating group, electron withdrawing group. So 1 and 2 are about the same, and compound 3 and 4 are analogous to each other. So from this, clearly we see that compound 3 and 4 have resulted in the most redshifted or noteworthy redshift at the wavelength lambda max at 495 nanometer in acetonitrile. So this redshifted spectrum shows the energy band gap in compound 3 and 4 has been reduced, in the molecule has been reduced. So the transfer of the electrons in this molecule 3 and 4 are easier. So now we compare with the rest of the compounds, compound 6, 7, and 8. So obviously compound 3 is the most redshifted one. So why compound 3 and 4 are the most redshifted one? So it might be due to the position of the nitro and amino group in that position for in molecule 3 and 4. So this kind of arrangement or attachment has provided better electron polarizability, which resulted in smaller energy band gap and caused more redshifted spectrum. Then comparing compound 5, 6, and 7, which are compound 6 and 7 are benzothiosyl derivative. As can be seen, there is a redshift or beta-chromic effect from 7 to 6 due to the different types of electron accepting group at position carbon 6. Compound 7 contains chloride, while compound 6 contains nitro. Nitro is a strong electron withdrawing group as compared to chlorine or chloride, hence compound 6 was more redshifted. Comparing 5 and 6, there is a slight redshift or beta-chromic shift from 6 to 5 due to the fused benzene ring in thiazole, benzothiosyl in 6 that might cause its lambda max shorter. Okay, now solvatochromism studies which were done via their absorbance in the UVV's range. As shown before, compounds 3 and 4 have the most redshifted lambda max. Both have the same lambda max, which is 495 nanometer in acetonitrile. Both were dissolved in 5 different organic solvents based on its polarity index from nonpolar to polar solvents. We can see from the graph and also from the color of the solutions, both are positively solvatochromic molecules. What caused this positive solvatochromic effect? It is because these compounds are highly polarizable dipolar molecules which strongly reacted to the surrounding medium polarity. In conclusion, 8 new dipolar thiazole derivatives have successfully synthesized. Compounds 3 and 4 have resulted in the most redshifted lambda max, show that they have more effective pi conjugation moieties for a push-pull system. And then for the solvatochromic analysis for 3 and 4, 3 different solvents polarities showed that they have positive solvatochromism, the large redshift lambda max, and positive solvatochromic effect showed 3 and 4 are promising candidates for NLO-related applications, especially for second-order NLO process, and also both compounds show good thermostability. I would like to thank Ministry of Higher Education of Malaysia for FRHS funding and CRIM UKM for research facilities provided. Thank you.